large program, with CTEL that has for goal to study the ionized gas in 35 close by galaxies using CTEL in 3 filters, the SN1, SN2, SN3. The main idea behind those filters is that it covers the main strong emission lines in the visible, and we can use them to probe the physical condition of the gas. Before I really dive into the subject, I want to mention that everything I'm going to show you right now has been done for half of the sample. And the second point is my presentation is going to be in 2 parts. The first one is going to be about data calibration, and the second one will be on the physics we can do with those recalibrated data. Okay. If we go from scratch, what we receive from CTEL is hyperspectral cubes. So it's AFU data. Pretty sure you all know what it is. But you basically have 1 image per wavelength. So that's a lot of data. It's 4 million spectra. Luckily, we have a nice fitting tools called ORCs that has been made by Thomas Martin right here, which allow to pass through each pixel and basically fit all the emission lines. So for example, here we have the S2 doublets and the H-alpha line. So we fit all those lines, and what we get at the end, instead of having data cubes, we get maps, which are much more convenient to use. So what type of maps do we have? We have a flux map. So here, for example, we have the H-alpha emission and the O2 emission. So in each pixel, we have the flux of the line that has been integrated. We also get the velocity, which is basically the position of the line. And we have the velocity dispersion, which is basically the broadening of the lines. So those can be used for kinematics and dynamic study. Okay. So we are almost ready to have ready to do science data. We still need to focus on 2 points. The first one is the astrometry, because while we have maps, it would be really nice that everything is super well aligned. And for extended sources, we kind of want to be able to do a pixel by pixel study. So we had to redo the astrometry. Without going too much into the detail, the main idea is that we now have a technique that allows to have below the tenth of a pixel in terms of precision in between our filters. So this is mostly for the center part of the field, but this is already well enough for the galaxies that are always in the center of field of view. And the second point on which I do want to spend a little bit more time are the flux calibration. So we went with Gaia, because I really think in terms of calibration, Gaia is completely changing the game, especially for a CTEL. Because instead of having one standard star, well, we can use dozens. So it's quite easy. With the Gaia XPy, we can directly select our object. Here, for example, it's NGC 925. We find all in the Gaia catalog, all the stars that have a calibrated spectra. We get these spectra, which are here. We convolve it with our filter transmission, and we can directly compare with our measurements. So here's an example for one field of M33 in the SN2 filter. On the x-axis, you see the Gaia measurement, and on the y-axis, you see CTEL. So ideally, what we would really like to see is x equal y lines. That would mean the calibration is perfect. However, this is not the case. We do find a really linear relation with very little scatter. So that's really nice. You see that, for example, in this case, we have 13% more fluxes than expected. So the coefficient of the line is directly the calibration coefficient. You need to divide your measurement with this to get the correct fluxes. Here's another example in the SN1 filter. We see that the linear relation is really maintained regardless of the wavelength. So that's actually really nice. Here, for example, we were missing 15% of our flux, which is actually quite important. And so I've done it for half of the signal sample. And if we check at globally the distribution, what we realize is that in the SN3 filter, we typically miss around 10% of the flux. It's 15% in SN2, and it's around 20% in SN1. This is actually a key point, because if you take the two opposite of the distribution, if you miss 40% in SN1 and you have, for example, 10% more in SN3, then your line ratio are completely scrapped. So this is really nice that we are now able to have a really nice flux calibration. The uncertainty we have on the fit is around 3%. This is a lower limit in terms of uncertainty, but it's still really very nice. And even if, I'm pretty sure the absolute calibration, the uncertainty is going to be between 3 and 10%, let's say. However, on a relative point of view, this is going to be absolutely amazing because we use the same stars to calibrate the 3 filters. So on a relative scale, we really can do a line ratio on a pixel by pixel scale now. So that's really nice. And now enough calibration. Let's talk a little bit more about the science, which go with the signals. So the goal with signals is to study the ionized gas. In this presentation, I'm mainly going to focus on two key points, I think, which are H2 regions and diffuse ionized gas. So I think you all know what is an H2 regions, but let's say you don't. Whenever you have a molecular cloud that collapse and form new stars, there are often massive stars, they ionize the gas. And so if you have a completely homogeneous gas, you're going to end up with a really nice sphere that we usually call the Strömgren sphere. However, and I wanted to show you two images. This is M33. This and this are two H2 regions. And as you can see, this is nowhere circular. And so there's many reasons it is not. So for instance, the cluster evolve with age. The gas is not isotropic. The density profile is not homogeneous. Gas is clumpy. There's turbulence. So there's many reasons that explain why the H2 regions are not circular. And therefore, it's going to struggle to do a proper aperture to get the H2 regions. So one of the solutions is to have a bigger aperture, so you're pretty sure that you have completely your object. However, if you do this, you have another problem, which is the diffuse ionized gas. So I wanted to show this example here, which is NGC 4449, which is a smaller irregular galaxy, which is completely embedded in diffuse ionized gas. The diffuse ionized gas has a very low density. It's typically it's below 1 particle per centimeter cube. It is ionized by many sources. It could be leaky H2 regions. It can be white dwarf of the older population. It can be supernova or turbulence. So you have many ionization sources, and one of the way to see it is in the line ratio. So depending on what's the sources, we're going to see difference in the line ratio. However, whenever you want to look at one H2 regions, you have this gas that's in between. It's like a big layer of gas, and you have your galactic disk in between. And so one of the solutions is to make an aperture. Okay, you have your H2 regions, it's integrated. You have the pollution of the diffuse ionized gas, and then you just try to find a background and try to extract it. It's nice, but how do you do whenever you have a complex regions like this, where basically in each region is going to be next to the other, or sometimes they're even polluting each other. So this is a real struggle to extract them properly. And with this problematic, we came with a new solution, which I am going to present you right now, which we call the nebulae, which is basically an algorithm that is made to separate H2 regions from the diffuse ionized gas. So how do we do? We change of paradigm. Instead of trying to integrate each region individually to nicely segment it and everything, we change our focus. We say, okay, we are not going to be able to do this. However, we might be able to extract it as a whole, and then we're going to be able to get the diffuse emission. How do we do? So we basically go in the galaxy, pixel by pixel. We go for the brightest object. We fit it with a Gaussian, and we extract it. And we go on and on and on and on until there's no more compact sources. And so this works under the hypothesis that regardless of your morphology, even if we take, for example, this filament here, well, we're going to be able to model it by maybe, 10 or 20 Gaussians. But at the end, whenever we're going to sum all those Gaussians, we're going to get back our structure. There is another way to do this, much more elegant, which is a wavelet transform. However, I don't know if someone here already used a wavelet. It's a real nightmare to find the correct wavelet and to find the correct baseline. We still are working on it. But however, might not be elegant, but it's actually working really well. So I have just a few examples to show you. Here is the brightest H2 regions of the galaxy. We model it with a Gaussian and we extract it. So that's our residual. We see that we almost well extracted this one. There's still a few, a little bit here missing. However, we're going to come back here and we're going to model this again with a Gaussian, extract it. And you see that in the residual, we end up with three points. guess what? We're going to come back again. We're going to go there. We're going to extract it. And that's going to be a residual, and so on, and so on, and so on. And so at the end, what we get from this, which is the H-alpha emission of the galaxy, we get two maps. You might see here that there is a few artifacts. Well, indeed, it's not a really elegant matter, so sometimes there's a few issues. And one of the main struggle with H2 regions, that's actually an interesting point, is that from the brightest H2 regions to the weakest, you go through more than 2 decks of luminosity. And that means that even if for this region, we almost perfectly measure it, with let's say a 0.1% of precision, well, this uncertainty is still going to be higher than the small region that is next to it. And so that's why sometimes we kind of see this type of artifact. Again, I think with the correct wavelet, I think we might remove of those artifacts. But again, this is a work in progress. I have a few images to show you what it's given. So for example, here is the NGC 4214. It's a bright irregular galaxy. This is the H-alpha emission. And this is the diffuse emission. So you really see that it's like turning the light off. On the other hand, you have the compact sources. So here, for example, it's sad we do not really see on the screen, but we do get our supernova remnants. We highlight the filaments and the H2 regions. So that's pretty nice. Here another example of NGC 1058, which is a spiral galaxy. Again, this is the H-alpha emission. Here's the diffuse, and here's the compact sources. So we really see that we really separate the two components. Now, okay, that'll start to be really interesting. The only thing we needed to do this is, because there one free parameter, which is the weight of the fit, and a map. So we have done it in H-alpha. Well, we can do it in all the other lines completely independently without any prior on the previous extractions. And if we really manage to separate, to split the two components, then we should see, when doing line ratios, that we should see some differences. So here is the BPT diagram for all the pixels with a signal-to-noise ratio higher than 3 for all the emission lines. For the NGC 4214, which is the irregular galaxy I just shown you. In blue, you have the H2 regions, and in red, you have the diffuse emission. So those are a BPT diagram. I don't know if you know much about it. It's for Baldwin Philip Terlevich. It's a diagnostic diagram. And so basically in this area, you find the gas that is ionized by radiation. And on the other hand, you find the gas that's ionized by shocks. So it's typically supernovae, AGN, stuff like that. So this is O3 over H beta, and here is N2 over H alpha, and here is S2 over H alpha. The two are very similar. They just are more or less sensible to different things. And what we see, which I find really nice, first of all, we clearly see a clear separation here in the channel sources. So you have one part that is probably ionized by leaky photons, and you have the other one that is probably ionized by shocks or turbulence. Here's NGC 1058 that has just shown before. So we see that right now it's a little bit lower in the BPT because of the metallicity. And we see that the diffuse ionized gas really spread out in this diagram. This is an effect of the metallicity. And we actually expect the O3 over H beta in the diffuse ionized gas to go higher with increasing metallicity. I think that's it for me. So as a conclusion, I'll say we now have new cubes to release with new calibration, realigned. I did not mention, but we can match the seeing really in order to have pixel by pixel studies. We have corrected emission line map also. We have a new DIGS map, so we can really, I think this is the first time we have a such map where we can really start to do science on the diffuse ionized gas, look how it behaves with the different sources. And that's it. Thank you.
Thanks, Sébastien. Any questions? Yes, Luke.
Nice presentation. I'm just curious, is the gas gravitationally bound to the galaxy?
This is a good question, and I have no idea. I would assume the ionized gas is gravitationally bound to the galaxy, but I don't know.
Okay, thank you. Sorry.
Okay, I'll go there first.
Thank you for nice presentation. I was curious if, I guess you showed a couple of objects here, but do you think this would extend also objects that have active galactic nuclei, like AGN emission? Because that would be a different, I don't know how that would affect the shape of the ionized region. I'm curious what would happen.
I'm very certain it will work on any images. Could be in astrophysics, but could be anything that has really two components, diffuse one and a compact one. I'd like to try on IGN to see what's the result. Yes.
And maybe if I can squeeze one other quick. Do you think this is applicable to other ISU maps, like Muse, for example, on the VLT?
So I don't know how the Muse data work, but assuming they have maps of each emission line, I think they should work. Yes. Or I would like to try, honestly. Maybe you have to tweak the scale and
Okay, next one.
physical scale of the pixels. So there's maybe a few little fine tuning to do, but I'm very certain it should work. Yes.
Hi, I'm just wondering about the calibration where you have.
You want me to go back?
Sure. It just seems like I'm surprised the uncertainty in that slope is as large as 20%, and I'm wondering what's driving that. Is that the Gaia fluxes are uncertain, or is it?
You mean why we have such a high difference here?
Yeah, like this large. So
I don't know where it comes from. Okay, to be honest. I do believe Gaia has really nicely calibrated data. We made some try, actually. I have some slide on it if you want. We did compare with other data. So we did a comparison with the HST data. So we went, there's a few maps we have for a few cubes. We have, so in this 4-14, we have the O2 emission, and there's a bit of H alpha in a few galaxies. So we compared the correction we had to make with Gaia or with HST. It is really well within the 10%. And in this case, the uncertainty really comes from the background subtraction in the HST data. It might be the way we are doing it. We did also a test with planetary nebulae in M33. We have 3% differences with previous methods. And another key test we made for M101, there's a few fields that overlap. So we did try to check if after the calibration, it was calibrated in between, and it's really working well. So I don't know where the issue comes from, but I think the main point is we can correct it now.
Any other question? If not, we're going to move to our next talk, but let's thank Sébastien again.